Good afternoon, everyone. Thank you for coming. I really appreciate it. This is my third reInvent, and I'm always staggered by the size of this conference every time. It's amazing. So again, thanks so much for coming. My name is Brandon Chavez. I'm a solutions architect, and I work on the Amazon Partner Network team. So that means I work with our technology partners to help architect solutions that solve problems for our customers. So today what we want to talk about is your options for managing containers on AWS, and there's quite a few of them. So we're going to cover some solutions that allow you to manage containers at scale and see how you can easily get started with these options. So it's my intention to give you the information you need to basically get started on your journey in evaluating these different options. And I really hope to present this in a very objective way and leave out really any subjective opinions of my own, because I don't believe it's possible for me to make recommendations that are applicable for any of you in this crowd right now. There's just too many different use cases, and everyone has to make this decision on their own. So what I want to do is kind of get started by understanding what is orchestration and why you might need it, and maybe give some context for why we thought this talk was necessary at all in the first place, right? So let's go ahead and get started here. So when we think about running containers on AWS very early on in that journey, you might think that this is just a really straightforward thing. We've all kind of used Docker before. If you're sitting in this room, probably you've played with Docker CLI. You might have built a compose file. You might have built your own image. And so early on, you might just think, I just got to run some containers on some EC2 instances, right? I spin up some instances. I log into the instances. I spin up the containers. What's the big deal? And you probably really like the deployment flexibility and the consistency of the packaging model. And you really want to leverage this in a way that also kind of dovetails with the advantages of running containers on the cloud. So I think early on in that journey, it's really easy when you're getting started. You run a couple of containers. You can manage them manually. You might even write your own orchestration. I talk to a lot of customers who do things like, well, we just write it all in CloudFormation and we do our orchestration that way, and it seems to work right now for the scale that we're at. But we're worried about how it might scale in the future because we're expecting rapid growth of our service. So maybe we need something purpose-built for this. We're not sure. And that's a good thing to start thinking about early on, because once your deployments start looking like this, I think it's safe to say once you're running a lot of machines and a lot of containers, things get a lot more difficult, and that's because this generally implies that you're managing a cluster. You're running a cluster of instances, and cluster management isn't the most trivial thing to do. So I would wager that you're probably not writing your own cluster management solution, and I'd also wager that it's probably not the best way for you to spend your engineering cycles. You don't need to reinvent the wheel. You don't need to go and build your own orchestration platform. You can totally do this with bash scripts and CloudFormation and solve some of these problems on your own, but I'd recommend against it, if I may. So you need a way basically to intelligently place containers on your instances that have the resources available to run those containers. So in order to do this, you have to know the state of everything in your system. So that means tracking and aggregating all of the individual resources from all the machines in your cluster, and then making them available, maybe via a common simple API, to run your jobs. So some information you might have to track, that would include, that machine up there in the corner, is it up and running? What about that machine down there? Does it have the resources needed to run my job? What about that job I submitted earlier this day? Is it still running? What are the results of the task? Did a task down here terminate unexpectedly? How do I figure out what happened? Do I have to log into that machine and look at logs directly? So there's a lot of things that happen as you grow and scale, and it can be pretty daunting. So we really need to find an appropriate tool to handle this for us. So, early on in your journey, you're looking around for options, and it's quite literally chaos out there, and there's like a giant cephalopod throwing your containers into the water, and other animals playing next to like a commuter rail train. So it's very dangerous, right? So AWS is probably out here somewhere in the middle of your container strategy, and you might not be sure kind of how all these things fit together. How do I get started? And this can lead to quite a bit of frustration, right? Early on, it can be difficult to figure out where to start and which product meets your needs. So I would like to console you just a little bit and suggest that you're not alone here. This is not a reflection on your capabilities or intelligence. This is a very reasonable problem to have. I spend a lot of my time focused on this space, and there's new solutions that come up every other week, and it kind of feels like you're really being left behind if you're not playing with like the new hotness, right? You're not touching the coolest new container tools, and what if I'm being left behind? What if I choose the wrong thing that's obsolete next week? It's probably not going to be the case. We need to identify what's good for our particular use cases here. So, I love this tweet from Brian Cantrill. He's objectively a very smart dude. He's the CTO of Joyent. And he posed this question sometime last year. Are we at peak confusion yet? He believes no, the confusion's still accelerating. Every single time that you look at, Hacker News, there's something else out there that you're supposed to take a look at. And if you're not using it in production, then oh my gosh. So, valid question. We need to get through the muck. So maybe the first question that we need to answer is, where are we going to run our containers? You might say, okay, we're going to run them on AWS, which is a great choice. And there's a lot of precedent for that. There's a lot of customers running different container workloads on AWS in a variety of different ways, just about every way you can think of for a number of different use cases. So what I'm going to do is just leave this flow chart on the screen, go get some lunch, check back in about 45 minutes if you guys have questions, and hopefully you're good. So I really don't think this is a good approach. I don't think this has to be some sadistic choose your own adventure game where the first step is literally evaluating your personal preference for pain and suffering. I don't think that's a productive way of going about this. So let's look at some of the options and see what we can do to help alleviate some of this struggle for you early on, and present some of the options that might answer some of these questions for you. So I think a really important aspect early on in this process is understanding that AWS has a really robust partner ecosystem that can help you with a variety of different challenges during your container journey. So because I work for the partner ecosystem, this is my chance for kind of doting on some of the partners here and talking about the cool things that they're doing. If we walk through some of the categories here, the first category here is foundation. And that's partners like maybe Docker, who build the Docker engine that you know and love, and they build an orchestration framework, and they build a registry. Or maybe CoreOS would be in foundation also. They build a container runtime called Rocket. They build an operating system optimized for running containers. They also build a container orchestration framework. SUSE, lots of props for a logo that looks good on a black background in this case. They build an OS optimized for EC2 container service. Rancher builds an OS optimized for containers. They also build an orchestration framework that works on AWS. In the monitoring category here, we have companies like Sysdig and Datadog, and their specialty is giving you very granular metrics about your containers with some historical perspective. Because your containers change, they come up and down so frequently, and they're very dynamic in nature, it might be hard to correlate logs for a particular error you were seeing yesterday, and that container hasn't existed for 18 hours, right? So Datadog or Sysdig allow you to kind of retroactively look and correlate errors and metrics with maybe what was happening in your infrastructure at that time. So looking at the container, looking at the application level logs. In CI/CD, it's in this journey, it eventually becomes very important to figure out a continuous integration and continuous deployment strategy. And we have a number of partners to help you with that. Shippable, Solana Labs, Circle CI, maybe CloudBees, they're the enterprise Jenkins company. They're run by the founder of Jenkins, the open source Jenkins. And they have integrations with a variety of AWS services. They can help you deploy directly to ECS or Mesosphere or Kubernetes, whatever it is that you're choosing to run your containers on. In the platform as a service category, we have companies like Convox, which is a PaaS offering that kind of helps you build containerized applications on top of multiple AWS services. So it runs on ECS underneath for running your containers, and then it also hooks into other AWS services that are useful, like KMS or RDS for persistence, and kind of abstracts this all away under a very convenient API. So this feels like a little bit of a digression in this talk, and it is, but I think the point I'm really trying to get through here is that the AWS partner ecosystem is here for you, and if there's a problem you need to solve in terms of containers, chances are one of these partners has something that can help you out. And this is critical. You don't have to blaze your own trail every single time you encounter a new problem. So let's get into the actual meat and potatoes of this presentation here. Let's talk about if you want an orchestration framework on AWS, what are your primary options? And I've chose 4 to cover today. And I think these are the 4 most common that we see on AWS. In no particular order here, we'll cover Amazon ECS, or EC2 Container Service, which is the service we've built for running containers at scale. We'll talk about a Kubernetes distribution, which is Tectonic by CoreOS. And Kubernetes is extremely popular on AWS, rapidly growing, and a lot of customers are using this. We're also going to talk about Mesosphere's DCIOS, which is based on the Mesos framework. And then we're going to talk about Docker Datacenter, which is the Docker native offering. So maybe that we've talked about what we're going to cover today. Let's address the original question of what is orchestration? What problems does it solve for me? Why do I need it? So if I was going to read you a definition from my slide notes, which I will, I would define orchestration as continuous automated scheduling, coordination, and management of complex systems of containerized components and the resources they consume. So looking at this diagram here, it's good to envision this as an orchestration layer that spans and aggregates your underlying compute resources and provides a layer of abstraction here that helps you to deploy and manage your applications and services and not care so much about the individual instances that are underneath the orchestration layer. So the functional result of having an orchestration layer is it exposes a single API to facilitate interaction with your services and your cluster. So you don't have to know about any of these resources here on the right-hand side. You simply specify your job requirements, generally in some declarative format, and you call the orchestration platform's API. And the orchestration platform uses its knowledge of the resources that are available and the constraints of your job, and it finds an optimal place to run this work. So if we expand the orchestration layer a little bit and maybe break it out by what the 3 main responsibilities are, I think the first here would be service management. So this would probably be a general set of capabilities to let you manage distributed applications at scale. So some of the functionalities that are required here are, I would say, some logic to ensure application availability. So maybe knowing the desired state of your application and ensuring it stays in that state. Maybe I need 4 of this particular container to run across AZs. Those are some constraints I've set. So I need my orchestration layer to help me maintain that desired state. We also need functionality to help us manage the lifecycle of that service. So helping us to upgrade or downgrade containers across our fleet when we're making changes to our application. And that's something that you might do dozens or hundreds of times a day, depending on how frequently you deploy. Because when you make new commits, you'll be building new containers and then deploying those containers to your infrastructure. So you need a way of doing that in a streamlined fashion. And then finally, we also need some way of managing the discoverability of this service. So this could be by checking containers into a load balancer, maybe updating a key value store, exposing health checks for our service, generally providing a way of saying, like, hey, I'm over here, I'm alive, and I'm ready to take traffic at this particular location, either doing that in a public-facing way or to other services in your architecture. So second is scheduling. And scheduling is the functionality in an orchestration platform that allows work to actually be given to the cluster. So there's a lot of different scheduling algorithms available, but they all essentially boil down to, I have a job, it has these requirements. They might be resource-specific requirements, availability requirements, like always prefer a multi-AZ deployment of work. Or something like an exclusivity requirement, which says that these 2 jobs, they can never run together because they step on each other's toes. And the scheduler submits these requirements to the cluster manager. So schedulers can also help you make changes to the state of a currently running service and perform actions like upgrades or rollbacks, and then determining how these changes should happen. So you might be able to give it some constraints about how you do a blue-green deploy, how much of a new container can roll out at a given time. Do you want to split your new deployment 50-50 with your old deployment so you can see if you're introducing errors. Your scheduler provides the logic that allows you to do these kind of things. Schedulers also generally understand scaling, so that would be changing the amount of current running containers in your service in order to handle load fluctuations. And they might do this in response to metrics that are emitted from like CloudWatch, for example. And then finally, your orchestration platform provides resource management. So the resource manager will understand what resources are in its domain and then aggregate all of these resources into a single pool. And we usually call the single pool a cluster. And that cluster might be divided into different parts for different workloads. But the ultimate goal here of a resource manager is to help you abstract away your entire data center or a bunch of instances and allocate resources to those underlying instances in a really fine-grained manner. So if I can quote the Mesos paper real quick, cluster computing frameworks simplify programming the cluster. So some of the resource attributes or some of the resources that you might be allocating here are different attributes like memory, CPU, and ports, in some cases GPUs, maybe disks. These are the three primary ones. And then finally, let's have a quick blurb on schedulers, different types of schedulers. So I think scheduling is a pretty important concept to understand because it's really central to all orchestration frameworks. So a cluster scheduler has a couple of different goals here. One is to use the cluster's resources efficiently. It has to work within the user-supplied constraints of your job. And then it has to schedule applications rapidly to not leave them in a pending state so you can understand which resources are available at any given time. Schedulers should also have a degree of fairness. And then finally, they should be robust to errors and highly available. So there's three main types here. The first is a monolithic scheduler, and this is composed of a single scheduling agent that handles all of the requests. And they're really commonly used in like high-performance computing. The monolithic scheduler handles one job at a time, and it controls all of the underlying resources. Kubernetes is a type of advanced monolithic scheduler. There's also a type called a two-level scheduler, which is what Mesos uses. And this is where a resource manager basically partitions the underlying cluster and makes offers to different schedulers based on these partitions. So this means that something called pessimistic locking is used during offers, which ensures that resources are not available or that are not taken before a job confirms that it needs those resources. And then finally, the last type here is shared state or optimistic concurrency, which is basically using an atomic locking mechanism. And this allows multiple schedulers to see the full state of the resources in the cluster. And the way that this works is essentially the first up-to-date claim on resources wins and secures those resources. And this is the model that ECS uses. So these concepts are really outlined in depth in like Google's Borg paper, which I suggest reading if you're looking for more information about this. But really, I'm just bringing that up because it's a nice segue into our first orchestration framework that we're going to talk about today, which is Kubernetes. And Kubernetes is not Borg, but it was based upon a lot of the learnings from Google running their applications at scale on the Borg platform. So I think a lot of our customers love Kubernetes. There are huge numbers of Kubernetes clusters running on AWS, and it's really rapidly growing. To summarize Kubernetes, if you're unfamiliar, it's a platform for running microservices at its bare minimum. I don't really want to tell you too much about like why you should or shouldn't use it, but if I have to call out some pluses or minuses here in this case, I think in terms of pluses, it really excels at application lifecycle management. I think it gives you a lot of nice control over how your application lifecycle is defined, and a lot of granular control over that. I think the downsides are that I think the Kubernetes community would generally agree that it's not necessarily easy to get started with or to manage, especially if you're a small team and you're unfamiliar with it. They're making strides in the open source community to address this, but right off the bat, it's not always the easiest. So talking about the architecture here, up in the top right, etcd is the backend data store for the cluster, which is a distributed key value store. The API server here is kind of the core of the system, and it's responsible for processing requests and manipulating the underlying state objects. And then the rest of the cluster management logic are basically a bunch of microservices that work with the API server. So On all of the nodes runs something called the kubelet, which is an agent. There's also something called the kube proxy, which does things like connecting your apps to the outside world or forwarding requests to the right place in the cluster. And then, of course, there's Docker as the runtime here. Your applications are scheduled together as pods, which can be one or more containers that run together on the same context, so they all land on the same instance, right? The same Kubernetes worker. And so Kubernetes upstream, or the open source project itself, it really provides you a bunch of things right out of the box. So it's got a command line, kubectl. It's got horizontal scaling across multiple instances in a single AZ. Kind of some niceties like service discovery and load balancing built in. But we think that if you're going to run Kubernetes in production, we recommend that you try to make things a little bit easier on yourself and consider something other than just running the upstream open source version. And I think our recommendation here is Tectonic from CoreOS, because it's basically upstream Kubernetes with some nice wrappers around it to make installing and managing Kubernetes on AWS much more intuitive. It does a lot of the heavy lifting for you. So some of these features are really important for running Kubernetes in production, in my opinion. So Tectonic provides things like an installer, a GUI for management, if you like GUIs, integration with like LDAP and provides role-based access control, and then some tooling for managing the actual cluster itself. So on AWS specifically, Tectonic helps tie Kubernetes into autoscaling. It's tied into some of our monitoring and logging and alerting systems. And you can use the Tectonic management console to manage multiple clusters of Kubernetes all running in AWS. Tectonic also comes packaged with CoreOS, as you might have guessed, given that it's produced by CoreOS. So this is an operating system packaged with Docker and it's kind of vetted against the version of Docker that's running in the release, which is actually a really nice thing. You really want to make sure Docker is vetted against the OS that you're running, because debugging some bizarre kernel panic that no one's seen before on Stack Overflow at like 3 in the morning and it's your production system is probably not for the faint of heart. So that's something that I would advise. And then CoreOS also provides some stuff like Core Update, which allows you to do rolling updates of the cluster itself. So managing the actual Kubernetes infrastructure with some of these tools kind of alleviates a lot of the heavy lifting for you. And some other functionality on AWS, I mentioned the installer, but this is great because it really bakes in a lot of AWS common sense into this installer. So it gets you to mostly a production-ready state right off the bat, which is nice. And then this Kubernetes installation is configured in a self-hosted fashion, which basically means using Kubernetes to schedule its own components across the cluster. And that's nice because then you can use Kubernetes lifecycle management tools to manage the actual components of the cluster, which is pretty cool. And then some other stuff like backing up the etcd key value store to S3, automatic encryption of secrets in KMS. That stuff is really great. The tool that allows you to take advantage of this is kube AWS, and it's basically what provides a lot of the integration. So it essentially takes a config file in which you specify some values, so things like what your DNS endpoint should be, which KMS key did you create for us to use, and then it generates a CloudFormation template for you. So based on this config that you've specified, it spins up a CloudFormation template, creates the user data for all the instances, and basically in about 10 minutes, you can log in and check out your cluster, and you're ready to start placing tasks on Kubernetes, which is great. So we have a reference customer for Tectonic here. This is Planet Labs. They do some boring stuff like launching satellites and taking pictures of the Earth. But really, they have a very challenging use case, right? So they're taking a whole Earth data set, lots of images, lots of data, and they were experiencing a lot of growth in their business, so it was putting a lot of pressure on their systems originally and on their teams. So they were experiencing challenges with things like application version drift, inconsistent packaging, inconsistent deployment mechanisms across different teams. And so they decided to move to Tectonic and adopt Kubernetes as their primary platform for deploying on AWS. So the result was they really streamlined their application packaging and their deployment model, but it gave their teams the flexibility they really wanted. It improved their ability to manage dependencies, and really at the end of the day, they spent a lot less time thinking about infrastructure, and the engineering teams could focus on their primary goal, which was writing software. So I'm going to try my best to make some generic recommendations here. I forgot to mention, everyone should, if you have a QR code reader, there will be QR codes that you can use to get routed to the best place to get started running this particular platform on AWS. So I think if you want a Kubernetes experience tailored for AWS, we would encourage you to consider Tectonic. It's also a good option if you want to purchase support for Kubernetes, which if you don't have a ton of IT resources to manage a Kubernetes cluster, this might be a good option. And then finally, if you want to consider an alternate container runtime like Rocket by CoreOS, this might be one of the only options at the present that allow you to take advantage of that. So I'm going to pause for a second. Hopefully everyone's got their QR codes here. I can come back at the end and we'll look at this. But this should take you to the documentation for getting the Kube AWS tool and getting started running this on AWS. So if anyone has it up and running by the end of the talk, let me know. I have stickers. So let's move on. Let's look at Docker Datacenter. I will say that Docker Datacenter is probably the relative newcomer here in this space. And Docker Datacenter is the offering from Docker themselves. So DDC is kind of a package deal that's built around, first of all, the Docker engine, which is the Docker runtime that you already know and love, but a commercially supported version of that. It also has an orchestration platform called Universal Control Plane. And then it's also packaged with their own private registry called Docker Trusted Registry. And so DDC is kind of all of these things wrapped together. The actual orchestration framework, though, is Universal Control Plane. So breaking down like the main components here, UCP and DTR. UCP is what is the cluster manager. And so like Kubernetes, it also uses etcd for state management. It uses Docker Swarm for scheduling. And it also packages up some really nice features like LDAP, some load balancers, and like native Docker service discovery. And then Docker Trusted Registry here runs as a cluster of 3 instances, and again has things like LDAP support, content signing, and support for like S3 as the backend, so you can store your images in S3 through DTR, which is a really nice feature. So if I have to generalize about DDC, I would suggest that it really includes a lot of bleeding edge features, especially in the container networking space. I think that's the one of the impressions that this product has really left on me. So if we break this down a little bit and look at the architecture, the UCP controllers here, there's 3, 5, or 7 of them, and they all run the UCP manager container. And then all of the swarm nodes or the UCP workers in this diagram here all run a container for the agent, the UCP agent. When you deploy services, they are running on your swarm cluster, although the UCP managers also can run services for you. And so when you deploy services into the swarm cluster, they're automatically checked into an ELB if you're running on AWS. And then they're made available across the swarm routing mesh, which is a layer 4 load balancer that basically allows you to receive traffic on any node in the swarm cluster on the published service port for that particular service, and then have it forwarded to the appropriate VIP for the instance that service actually runs on. So it'll just automatically forward your request to the appropriate node in the cluster, which is nice. There's also kind of a new experimental feature called the HTTP routing mesh, which allows you to do things like forward L7 HTTP virtual hosts to the published VIP for the services. So you can configure services to have CNAMEs. When a request comes in for that CNAME, the routing mesh automatically forwards it to the service listening on the right node at the right port, which is quite nice. Diving into UCP a little bit more, the control plane itself, I think it has a really nice GUI, which is kind of a shallow thing, but I think it's really nice to look at. Maybe my personal favorite here. And you can do all of the management of your cluster through the GUI if that's something that you want to do. To manage it through the Docker CLI, there's a nice little thing where you can download a bundle, which gives you certificates that you plug into your local Docker CLI, and then all of a sudden you're communicating with your UCP cluster manager. And so when you do Docker run, it's actually scheduling it for you up in your cluster, which is pretty cool. Other interesting things, there's a built-in content trust mechanism which verifies the publisher of an image and ensures only signed images can run, which is a really nice feature for security. And then UCP also allows you to use custom SSL certificates, LDAP support, role-based access control. It has a built-in diagnostic tool which allows you to basically dump the logs from all of the nodes in the swarm cluster and look at them in one place. And then, of course, logging of everything is supported with AWS CloudWatch logs. Actually, I should note that if you're running Docker at all, there's an integrated driver for AWS CloudWatch logs. So even if you're just running Docker run from the command line, you can push your logs, all the standard error, standard output to CloudWatch logs, which is great. So we actually have a Quickstart for Docker Datacenter, and Quickstart is a program that we run that we work with partners to build kind of like a reference implementation of their product on AWS. So we kind of go through the motions of standing up this product in kind of a best practice way. So you can impress your boss by clicking the launch stack button. It's a CloudFormation template, and have it up and running in a couple of minutes, probably about 20 minutes on average. So when we deploy DDC into AWS, we deploy it into a VPC, so we create a VPC, or you can use your existing VPC. There's 2 availability zones with 2 public and 2 private subnets across them. There's elastic load balancers. There's 3, one for the front end of Docker Trusted Registry, one for the front end of UCP, and then an ELB functioning in TCP pass-through mode to forward requests to your services running on the Swarm cluster. And then all the necessary networking underlying stuff like NAT gateways, and we take care of all that for you. So we're going to zoom in here on the private subnet and look at what the configuration of the EC2 instances look like. We have, by default, 3 DTR controllers, 3 UCP controllers, and they're kind of irregularly distributed across the availability zones here. And then the Swarm nodes run in an auto-scaling group across both of the AZs. So cool stuff. Oh, I didn't give you guys a chance. Never mind, just kidding. Thought I missed the QR code. I didn't. Our reference customer for Docker Datacenter is ADP, and they were really interested in gaining more efficiencies and reuse of code by moving away from the monolithic model of deployment they were using previously. They were running on OpenStack, or are running on OpenStack for their private cloud, and they use AWS for their public cloud. So they needed a platform to help them migrate hundreds of monoliths that served hundreds of thousands of customers to a microservices model, also while migrating to the cloud. So Docker Datacenter enabled them to start implementing some microservices and continuous deployment, continuous integration practices, get their DevOps teams up and running, while running simultaneously on-premise and in AWS. So my recommendations here, you should use Docker Datacenter if. I think the Docker native stack is very important to you. If you want something that's all built by Docker, this is obviously your option. If your development workflow is built around Docker Compose and the Docker CLI, this is another reason you might really consider this. The ease of plugging in UCP as a cluster manager behind the local Docker CLI is great. And then finally, if you want commercial support for the Docker engine, this is basically one of your only options at this point. So QR code for Docker Datacenter, the Quickstart on AWS. This will take you to the Quickstart page. There's a deployment guide and a CloudFormation template, and this can have it up and running in about, I think, 20 minutes or so. So the next framework we're going to talk about is Mesos and Marathon. And Mesos was originally developed to perform fine-grained sharing of resources across different frameworks. And it was built because this is kind of a tough problem to solve. So the purpose of Mesos was to provide a scalable and efficient system that supported a wide array of different frameworks. And so some of those frameworks might be used for running Docker applications like Marathon, for example. And other frameworks are focused on big data. So you can run things like Spark or Hadoop or Elasticsearch on top of Hadoop, or on top of Mesos. So there's 4 elements, main elements here to a Mesos cluster. The backend data store is Zookeeper, which serves as a persistence layer and helps with leader election for a master. Marathon here is the framework that we use that starts and monitors and scales your applications running in containers. And then the Mesos master here is what's responsible for aggregating resource offers from all the nodes, all the agent nodes in the cluster, or the Mesos slaves here, and providing them to the registered frameworks. So when the Mesos master fails, maybe it crashes or goes offline for some reason, a standby Mesos master is promoted automatically without disturbing any of the running services, and Zookeeper is kind of responsible for rapidly electing a new leader, and essentially it can survive failure of the master node with very little disruption. The Mesos slaves, or the agents, pretty clearly are where your actual services are running in the cluster, where your frameworks run tasks. A task is the core unit of work that's scheduled by a Mesos framework and executed on one of the slaves. So DCOS, or Data Center OS, is an orchestration tool built around Mesos as the backend state management tool, and it's packaged with a Docker scheduling framework called Marathon. So Marathon gives you a GUI for managing services and other frameworks on DCOS, and there's a pretty cool DCOS CLI that allows you to manage the cluster and the things that are going on within Marathon. So other interesting components of DCOS, I would call out the admin router, which is like an open source Nginx configuration that provides like authentication and proxy to your DCOS services. There's a tool called the exhibitor, which configures Zookeeper during installation, and then it provides like a little web UI to Zookeeper. There's a tool called Mesos DN, which provides service discovery. So it allows your apps and your services to find each other by using DNS. There's also something called Minuteman, which is an internal like layer 4 load balancer that ships with this service. I think the most unique thing about DCOS in this case is the universe, which is the first thing we're calling out on the slide here. And this basically allows you to install a number of different frameworks onto DCOS. So you can run Cassandra or Jenkins or Hadoop, as I was mentioning earlier. On the same cluster, you're running your Docker containers, all your microservices. This is a really unique thing, and this is not something you can do with any of the other frameworks right now. So if you're really focused on having one cluster that runs everything and like really hammering home on the efficient resource utilization or resource density approach, then DCOS is kind of stands alone in that regard. And so this is unique because generally you would have a cluster for Spark, a cluster for Kafka, a cluster for Cassandra, and that's because these are distributed systems themselves, and they really have their own scheduling logic, and they really want to be able to grow and shrink their footprint. So they usually get their own cluster because you want to avoid resource conflicts. So it's very interesting that DCOS allows you to do this. So the DCOS approach, they turn your whole data center or a big group of resources into basically one giant computer, and then all the components of your app can be pulled. So again, it's interesting if you want to run all of these things together. Very unique. Finally, I'd say that Mesos has been around for quite some time. The Mesos paper itself was published in 2010. One of the Mesosphere co-founders published this while at Berkeley. And this paper kind of applied a lot of lessons that were learned at Google and Facebook on some of their internal large-scale platforms. So then the technology, the Mesos project was applied at Twitter, it was applied at Airbnb, where a couple of the other co-founders of Mesosphere applied the technology to resolve different infrastructure challenges. So you have all these people coming together who have had experience with this tool at large scale in different companies, realizing that it solves a bunch of problems, and they came together to form Mesosphere and the DCOS project, and to use it to solve your challenges in running containers at scale. So Mesos itself has been in use at a large number of enterprises, a variety of different use cases, even before the DCOS project was launched. I think in 2015, DCOS launched. It's open source, Apache 2.0, and it's been contributed to by something like 60 different companies, which is quite interesting. And then finally, Autodesk is our reference customer for DCOS. And so Autodesk has essentially built an internal cloud platform on top of DCOS and on top of AWS that allows them to get extremely efficient resource utilization. And so they run this internal cloud platform that a bunch of different teams deploy to many times a day across 3 different AWS regions. So DCOS helped them, first of all, streamline this deployment process. They can deploy new builds of software in about 40 seconds. And it also gave them dramatic cost savings. This is a metric that we really like. Moving to the internal Autodesk cloud platform, by building this, they were able to increase their infrastructure density or move to about 66% less instances than they had originally, and then reduce their overall spend by 57%. So we love talking about successful cost-saving measures. And so I will say, this first one is definitely in jest, but if you prefer technology that's kind of been around for a while and it's been in production in a bunch of different large enterprises, definitely take a look at DCOS. If you want to take advantage of the DCOS universe and manage big data applications on the same cluster as you're running your microservices, DCOS really stands alone in that regard. So QR code, take a look. This brings you to a CloudFormation stack that will launch DCOS fairly quickly for you. I think it's about 10 minutes, and that'll be up and running in your AWS account. And then finally, last but not least, this brings us to Amazon ECS, which is a tool that we've built to help customers manage containers at scale on AWS. So we built ECS to kind of help address some common issues with running containers at scale, and then plugging those containers into the rest of the AWS platform, which is challenging to do in some cases. So we want containers to be first-class citizens in AWS, and we feel like ECS is the vehicle to elevate them to that status eventually. So looking at this infrastructure diagram here, the first thing I need to point out is that ECS is a managed service. So AWS runs the state management engine and exposes all the information about your cluster through an API. So in the bottom box here, all of these things run in AWS. And then in the dotted line boxes, all of these things run inside of your VPC, and you can configure the networking and the instances as you like. But one thing to point out is that all the instances in ECS need the ECS agent installed in them, which runs as a container, and then it facilitates communication between the ECS API backend and the Docker daemon locally and all the instances in your cluster. The ECS optimized Amazon Linux AMI includes this pre-installed, as do a couple of the other different OS options, including SUSE, Rancher OS, and Core OS. So they all have the ECS agent pre-baked. So ECS is a service that will scale with you. It's managed. We've run some scale tests that show, I think over a 36-hour period, or was it a 72-hour period, we were able to scale our cluster up to like 1,500 instances with basically no impact on the response times of the API. So that API is really built to scale with you. And then because we expose the cluster state to you via APIs, you really have full control over your cluster and how your containers run on that cluster. And then finally, because it's a managed service, we provide all sorts of hooks into other AWS services with ECS. So you've probably seen this recently with some of the things like IAM roles at the task level, integration with auto-scaling for scaling your services, integration with the application load balancer, CloudWatch logs, and so on. So we intend to continue to add these types of features, and as I stated just a little bit ago, we really want containers to be first-class citizens in AWS. So looking over some of the components of ECS, starting at the top left here, there's a task which defines what containers should run and how they should run, and all the containers in a task run on the same instance. The task definition allows you to define, so a task definition is the definition of how all your containers should run. The task is the actual running implementation of that. The cluster, you can have multiple clusters in ECS. They're each their own namespace, and they're just essentially a pool of EC2 resources that run together. There's a cluster manager that aggregates all the cluster resources in the back end and the state of all the tasks. We have a scheduler that actually places tasks and considers your availability requirements for your service and the state of your cluster. And then finally, the agent, again, is what actually coordinates the EC2 instances and communicates with the back-end agent, or the back-end services. The basic workflow of running tasks on ECS are you take a task definition, you call the run task API, or you tell the service scheduler to create a service for you. The scheduler confers with the manager, asks, I have this job with these requirements, where should I run it? The manager then forwards the requirements to the cluster. The ECS agent parses the task definition, unpacks all the Docker commands, and then runs it locally on the instance. So a couple of case studies. First of all is Expedia. They run a tool called Primer, which is their internal deployment platform on top of ECS. And this platform supports like 200 different microservices and internal applications across a couple different ECS clusters that scale in response to their performance needs. So they've built a continuous integration platform that allows them to deploy directly to ECS very quickly across a bunch of different teams. I probably won't dive too deeply into this. If you want to learn more about how Expedia uses ECS, they spoke about their infrastructure and their continuous deployment pipeline at reInvent last year, so you can definitely find that on YouTube. And then one more case study, just because I have a little bit of time here. The Amazon Personalization team is a team that's responsible for when you log into Amazon.com and you get recommendations for a book you might want to buy. They're the team that's crunching all these big data sets about customers and what they've bought and what products are available, and then makes recommendations to you based on what you might actually want. They're actually generating these recommendations using GPU instances and scheduling this work via ECS. So they're running ECS clusters full of GPU instances, and they're throwing these massively parallel big data jobs onto these clusters, and then having the output data stored in S3, which is very interesting. So we've written a blog post that demonstrates how you can use GPUs from within containers. And we've got a CloudFormation template that demonstrates how you can kind of package all the necessary NVIDIA CUDA libraries inside the container and on the host to allow your containers to communicate with GPUs. So finally, my recommendations for ECS. You should use ECS if you want to manage service that scales with you. If you want to leverage more of the native AWS integrations like IAM roles or application load balancers, ECS is a good option. If you really want to build around the AWS native tooling like the AWS CLI, SDKs, CloudFormation, ECS might be for you. And then if you want to leverage the ECS partner ecosystem, it might be a good choice as well. So if I have to make a conclusion here, I think I will. I'll just say AWS is a very rich ecosystem. We support every major orchestration framework, and we see customers being successful with whatever orchestration framework they're using on AWS. Whether you're using ECS or a partner-built solution, really our goal is to build, offer you the best possible solution on AWS. And so if you are running container workloads, please think AWS first. So we have a little bit of time, about 15 minutes left. I'm just going to hang out down here, Mike, take some Q&A, and I have some stickers for our new open source project blocks. Thanks, everyone.